Thank you for the invitation. Thank you for the opportunity to present what I consider research. It's carried out together with Sergei Volov, one of the organizers today. And I have a fairly lengthy talk, so I will try to go through it all. I first want to set the stage tonight. Sorry, it's not here. So a bit of history and why this is such a complex research topic. Then I want to go, that's the bulk of the talk, into actual what I consider case studies. And then some concluding remarks that will be brief, hopefully, at the end about some more generic remarks. So this is about Majorana fermions. It's actually a beautiful story, a story that captured me when I started the research back in 2010, and I still find it a fascinating story. So the Majorana fermion is a highly mysterious particle, and the man himself is also very mysterious. You can read all about it. He disappeared. The particle is mysterious because as a fundamental particle, it has never been found in nature. Part of that is perhaps because it's a particle that has very little measurable properties. It's equal to its own antiparticle. And we love to use this analogy, the painting by René Magritte, where it's also very mysterious how the mirror image of the person can be equal to itself. Now, how did this enter solid state physics, condensed matter physics? That is a decades-long development that started in the 70s and then sort of accelerated from the late 90s, early 2000. And this has a really solid theoretical foundation. These are well-known, well-understood models, toy models, I should say. And what they predict is that the same field equations in particle physics can be applied to condensed matter systems, and one can get the same quantized solutions from it, quasi-particles now. No longer fundamental particles, so the electronic state, collective behavior of the condensed matter system. So this evolved in the years 2000s and actually became increasingly more realistic. And by the time of the start of my PhD, there was a proposal out there. It is 13 years ago now, I think, roughly, that this appeared at the March meeting, more or less. And that it looked like we could implement it. Now, another really exciting aspect of this research, genuinely exciting, is that these are different from, fundamentally very different, richer almost, I would say, from the fundamental particle physics, from the elementary particle physics version. These Majoranas, particles in quasi-particles in solid state systems, they have a very peculiar property. If you have an ensemble of them in a system, they form a quantum ground state. And by moving the particles around each other in the terms of moving their world lines around each other, you're actually changing between different ground states of these particles. And from an informational perspective, from a quantum computing perspective, this means you can encode information in the quantum ground state. And by moving the particles, the world lines of the particles around each other, you are actually performing a quantum computation. This process is called braiding because of the intricate pattern that the world lines form. And it's supposed to be resilient to noise because the pattern itself can be deformed and shaken, but to break the pattern, you need to cut strands, basically. So there's this combination of beautiful fundamental physics and potentially technologically attractive applications. And this was all known in 2010 already. I learned about this at the start of my PhD. So we set out to implement this research. It was a very exciting time with the team, real team effort, hard work, but we got early results after 1.5, 2 years in, got published, deserved a lot of exposure. So all looked fine. Then, as it turned out, and it's the next topic I want to put emphasis on, is that the research turned out to be very complex. And how can we understand this? So that's very typical in condensed matter, of course, is that toy model serves as the inspiration. So we have a simple formula with a bunch of terms. And then as an experimentalist, you look at that, how can we implement that? So what do? You look at all the various systems these terms represent. So what do we need to add? Superconductivity, complex semiconductors. These need to be made, these complex semiconductors. So material synthesis is what you need. And you need electronic nano device fabrication to shape it into the right geometry. Then you need to do cryogenic measurements. So this is actually very hard to make. And it's a real challenge as a team to get this done. And I can really confirm this. I've done this. It's hard work, but it is possible and you can make them. But it comes with the typical troubles, I think, that are well known in this type of research in condensed matter physics. Individual devices cannot be exactly reproduced. If you make your device so complex, it means you have many experimental parameters, typically about 5 or 10 knobs that you can turn. Makes the experiments complex. It's fairly costly to make this. The combination of fabricating the devices, assuming you have the facilities in place already, and having the setup, I think it's easily order 1 million for one of these experiments. And the measurement itself is highly complex, takes months. So what this amounts to is that it's hard to do statistics. It's hard to gather many data sets from many nominally identical devices. The other thing is that everybody is fully aware of this, I think, experimentalists and theorists. You never implement a toy model. You do something inspired on the toy model, but it's not the same. It's something different, something way more complex, something real life, honestly. It's like a cartoon versus the real thing. So that also means that theory has to and can develop itself by making the theory models more complex. So typically in our community, this means that you go to lattice models where you do complex numerical modulations, where you simulations, where you model your device as realistic as you can. You introduce more and more variables to try and map your model to the experimental reality. And of course, this is finite what you can achieve. It's infinitely extendable in principle, but it's, you know, beforehand, it's impossible to fully simulate a device. It's just not possible. It comes with programming complexity and computational time. So the same deal there also theoretically. Resources limit you in the end what you can do. And this begs, of course, the question, and how do we connect the two? How do we bridge this gap? And this is very challenging, actually. There are no established protocols for that, as far as I know, in our research in condensed matter physics. At least not in those subfields that I'm aware of. And this, I think, immediately lead to the major pitfall, and regardless of this is theory or experiment, is that there is a tendency for extreme fine-tuning and biased data selection. And why is this such a big issue? Because potentially viable alternative explanations actually do exist, and we are aware of them. So this leads sort of towards the end of my PhD, and I want to use this particular, which is sort of a counter example to the physics we are after, this experiment to introduce you to some of the typical data. So what you can see here in all these color plots is electrical conductance, so the differential differentiated current. Oops. That's a color scale, so red is high conductance, blue low conductance. Horizontally, there is typically a parameter varied, so it can be a gate voltage, can be a magnetic field. Vertical axis, we have bias voltage, which translates typically to energy, more or less, one-on-one. And the point is that for Majorana fermions, we look for something that sits in the middle here at 0. So the conductance is low here because this is a superconducting system, so the spectrum is gapped. And we want to sit here in the middle and find a high conductance there because we have this special Majorana state sitting there. That's not enough. We want it to be robust. We want it to be insensitive to minor variations or even major variations of this horizontal axis. Now, why is this such an important experiment? I think to our community, the authors implemented a very similar device, almost identical to the devices I made in my PhD as a student. And what they found was that also these states, which are clearly discrete states that move slowly, gradually together, that they can also linger for a little while at 0 energy, at 0 bias voltage, and mimic the behavior of Majorana bound states, Majorana fermions. Now, this was I think the whole community had digested this a little bit and accepted this. That took a couple of years. It took me towards the end of my PhD, 2015 or so, to I think, start embracing this idea. I moved out of the actual research topic. For my postdoc, I did something else, also in CondMat, but not the same topic. But then, of course, you keep watching your old field. I kept talking with Sergey, etc. And what we noticed that more and more claims are being published, follow-up research on our own research, but in some, looking at the papers as published, listening to the talks, not everything added up. And that brings me to my first case study, so to say. That's actually from my own PhD research group. This is about a paper which has been redacted in 2021, I think. And it was an important paper in the field. The claim was that a special type of zero bias conductance, namely the conductance was quantized now. You can read it here. The height of our zero bias peaks remains constant despite changing parameters. That indicates that it is quantized, and that was a hard prediction from basic theories that this should happen when you have a Majorana ferry. And this is how that looks in the paper as published. You can see that upon applying a magnetic field, one of the necessary things to do to make Majoranas in these nanowire devices, you can see that there is the conductance is here going up. There's these states coming down that form a zero bias peak, and it plateaus for a little while here before dipping down again. So that's as a function of magnetic field. And you take a crosscut, and you see a plateau also as a function of gate voltage. So it looks good in the relevant parameter space as something stable, something robust. So we asked for additional data because we had questions, got some in the form of a PDF file with color plots in it. Later down the track, also numeric data was shared, but initially when we performed our analysis, it was based on color plots of the data. And basically then we spent a couple of weeks stretching and matching graphs between the paper and between those between the additional data files shared with us, the PDF file with the color plots. And really, I think the main find and the most striking find is that for relatively small variations of parameters, some are a bit larger than others, but nominally this is all in a similar regime. You can see all these panels. This is always magnetic field on the vertical axis and bias voltage on the horizontal axis. Now I flipped the plot here. And you can see that you have these states coming together, forming the zero bias peak. What you can see that sometimes it appears as a crossing, sometimes it lingers a little bit, but you have this, this somewhat consistent behavior across all of them. And the point is that actually only 2 of the plots that are present show a conductance of order 1 times the conductance quantum, the value you need. Most of them show a higher or a lower value. A factor 1.5 different, more or less. So this is a case of critical data omission. I think if the community would have seen all these plots, we would not have believed that the peak was quantized. Now, if you look at the gate dependence, the other parameter that was varied, you can see it took a bit of detective work, but you can match up all the pixelations in this data set up here and down here. You can see that matches with the pixelation in the published figure, but there's also differences. So there's been cropped, so the data set is cropped, and there's also this section in the middle that's been cut out, and this was non-disclosed. Now, why is that important? Because if you these discrete jumps here, they're very common in these type of devices, and we understand them as random charges jumping around a little bit in the devices. It's sometimes a statistical process, just happens. Sometimes it's because you change a gate and then a charge trap empties or fills. And what they do, they reset somewhat the axis. They change the local potential landscape a little bit, so they affect your physical phenomena that you're trying to observe. Now, if we would have seen that right upon basically peaking, it immediately dips down again when a charge jumps, this would have been significant because it means that, what stops it from jumping all the way across here? Maybe there is no plateau at all. In fact, you can see here on the right side that it looks like the peak is splitting again. So perhaps all there is in this data is that you just have these 2 states, crossing a little bit, touching each other.
Sorry, Vincent, I think we're unable to see your pointer. If you have a pointer, we're not seeing it.
Oops, 1 moment. Thanks for pointing that out. Yep, can you see it now? Yeah.
Yes, now it's good. Thank you.
Yeah. So I was indicating these pixels here, and these are the discrete charge jumps that I mean. So you can see that cutting this bit here and cutting this bit here actually has an impact on the visual appearance of the phenomenon. Now it looks like a much more extended feature. Whereas in reality, if you look this as an experimentalist, if you have some experience dealing with this, you start to have questions: is this actually anything robust in the gate axis? This is another very peculiar panel. Is this small panel in figure 2E? What is done here, that you take horizontal line cuts in the plot, one at zero bias, where the peak sits, one above the superconducting gap, so at finite bias. You take the conductance values and you plot them against each other. So these values here correspond to this curve, and the vertical values here correspond to the curve in the center. And what you can see, that is the point of this figure, is that this is really flat. While the conductance here is rising, the conductance outside the gap, the conductance in the center of the gap where the Majorana peaks is supposed to be, stays flat. And the first striking thing is that if you compare another panel in the paper, you just compare them, you can see that about 70% of the data were excluded in the making of this panel. So when we got the numerical data, we could replot this. And what you can see, so this is basically replotting all these data points and keeping the same scaling of the axis. Okay, so that's another feature here, is that this is very different scaling compared to that one. What you see now is that this is basically a scatter plot without much flatness in it, if you accept that all points are data, but the yellow ones are the ones that constitute this curve. Okay, then you can even try to not take this curve, but the opposite one at the opposite bias, and you get yet another different shape. And you can see that there's actually more spread now in the superconducting conductance compared to the normal conductance. So in other words, there is no plateau here. And this was basically a combination of omission of unfavorable data points and a misleading scaling. And the last example I want to use from this work is figure 3, where they show the conductance in the center again of the peak. And this is a very strong statement written about this particular curve, namely that the zero bias peak comes back up to the quantized value, which is 1 in this curve, and does not cross through it. So something could affect it to bring it down, but it does not cross through it. And right at the point where the curve in the paper ends, the full data set continues, and you see that it crosses by a factor 1.5 through the actual value. So you can find there's some more details. I've shown you some striking examples, but you can find that in our independent analysis, and there's also an independent expert panel which confirms our findings, I must say. And this is a second paper, and this is mostly a material growth paper with actually interesting growth in there and interesting advances. But to make it really the breakthrough, I think, that made it into Nature, they needed also confirmation from electrical measurements, electrical transport measurements. And of course, they find in the paper that the device, that the material is great and that it is suitable for, observing Majorana fermions, establishing them, and then subsequently braiding them. That is the storyline of the paper. However, the paper figure 4 and some of the supplementary data that reports the electronic transport measurements, again, it is suffering from significant data omission. So cropping, but also lines have been deleted, to the effect that these bright vertical stripes that you see here are not being shown. And these are widely known in our community, and they are typically associated with uncontrolled, random, unwanted quantum dot features. It is localization. So it is the opposite of having a very clean device through which electrons can move unhindered. Instead, electrons are obstructed by potential barriers and they localize. And this basically means that, well, the growth is, of course, what it is, that is true. The electronic characterization measurements are not reliable, and this was the cause for the paper to be retracted. Now, the third example I want to show is, because it's slightly different in flavor, I think, it is selection of what devices to show in the paper to make a claim. So this is a fabrication run of 20 devices, where 4 were selected for inclusion in the paper. And what is significant here is that the ones selected don't show clear vertical stripes, but the ones non-selected, many of them do show these stripes. And again, this is because of generally understood due to unwanted quantum dot formation, and the claim of the paper is that this is not happening at all. Now, when you see this happening, when this occurs, then you need to ask yourself the question, why do I then select these devices into the paper? And this question has not been answered well in the paper. yeah, I can't go into all the details of that. You can find that in this Zenodo analysis. Yeah, so this paper is under investigation. We have recommended it to be retracted. I'm a co-author actually on it. I wasn't aware of these issues at the time of publication. And yeah, whatever happened to it, I want to retract my name from this paper. So what is the status here is that there has been no evidence. We did not find anything of data fabrication or data falsification at the basic level, but there were a number of undisclosed data manipulation steps that had significant impact. The most impactful aspect, in our opinion, is crucial data omission, so selective biased representation, and this has caused unsupported claims. So the current status is that the 2 papers retracted. We have recommended 2 additional ones for retraction. There's a number of additional papers, about order 10, I think, that we think should be investigated. Some do raise serious questions. And thankfully, Delft is releasing more and more raw data, although it is going very slow. But yeah, it is happening slowly. So I hope that in the near future, this can be closed, this topic. The second case I want to show is from a different institute, but very similar type of device. So now we again have a one-dimensional nanowire, but it is covered conformally with a superconducting shell. Actually very interesting, nice devices. Cool to study, I think. If you penetrate the cylindrical shell with flux and you put a flux quantum in it, the theoretical prediction is that you get Majorana fermions in these wires for odd flux quanta in there. So we had some questions about this paper as well. And we requested additional data from the journal, which we eventually then got some additional data, and we looked into it. So the main claim of this science paper is actually has nothing to do with Majorana. So it's purely phenomenological. The claim is that this is again a map of conductance. So dark is low conductance, bright is high conductance. Here now we have flux on the axis, and here we have bias voltage. So energy, if you wish. Here, for zero flux and low flux, when we don't have a flux quantum yet, we have a superconducting gap that slowly closes. And then as you put an integer number of flux in there, it reopens again. It's a beautiful effect. It's known for quite a while now, but it's really nice to see it in these mesoscopic devices, in these nanowires. But the statement is that every time you have 1 or 3 of these flux quanta in them, so the odd lobes of this pattern, there is a robust zero bias peak. So robust against magnetic field variations and gate variations. So the upshot is that this is not generally correlated with these oscillations. So we find in the same device, we find also examples of split peaks. In another device, which is nominally identical to the same device, we find a fork. So first it forks and then it becomes a zero bias peak. In yet another device, which is considered a negative device in the paper, there is also no zero bias peak here. So these 2 plots are from additional data that were not present in the original paper. So if I zoom in a little bit more on this feature, there is a strong statement about the behavior in this first lobe at finite magnetic field, namely that this zero bias peak, this is from the paper, this zero energy state it represents, is present throughout the tunneling regime. Okay. Now, if we look at the more extensive data shared with us, we find actually that the gate voltage range is not significant. We find instead that the blue line here represents the gate range. The 2 measurements are not exactly identical because of a charge switch in between. What we find in this particular scan is that the yellow boxes contain a zero bias peak and the green boxes don't contain a zero bias peak. And okay, this is the high conductance side, so who knows what happens really. But here in the tunneling regime about which the claim is being made, actually for most of the tunneling regime, there is a split peak. There is no zero bias peak. And this is in plain contradiction to what is written and shown in the paper. Another questionable aspect is what is a bad device in this research? So device 5 is being considered bad There's some reasoning behind it. One aspect is that it doesn't show the desired feature, the zero bias peak in the first lobe. The other one is that it shows these discrete states in the superconducting gap at zero magnetic field, and then there is a reasoning behind that. However, device 3 is considered a good device in the paper, but this large data set was not shown in the paper. And what you can see is, as a function of gate voltage, it's arguably messier in terms of states that are crossing through the superconducting gap compared to the other device. So what does a positive reproduction device mean versus a negative one that contradicts or that is a negative result in your study? What is really important in this case is that there have been independent reproduction studies. So this group from IST Austria, the authors here, they have actually obtained the identical nanowires from the same, nominally identical, it's not the same wire, of course, you cannot reuse them, from the same grower, but it was the same growth batch, I believe. So they made nominally identical devices. This is the closest you can come to reproduction in our community, and they performed the same experiment. And that it is a reproduction study is basically clear by looking at the data itself, because if you look at this typical pattern, gate voltage versus bias voltage, and you look at all these winding states inside the gap, that's essentially the same as what you see in most of these devices when you look at the extended data from the work from the other team. Now, what they find is that, it's in our opinion a more extensive study, more data is shared at least with us. What they find, they put the full spotlight on these winding states, and they show that indeed for very small, but somewhat extensive parameter ranges, it's still of the order of hundreds of millivolts, you can find lingering zero bias peaks. But it's completely interpreted in this paper in the framework of these trivial Andreev bound states, which cross as a function of parameter changes in the experiment, and then sometimes linger a little bit at zero bias, mimicking the behavior you expect for Andreev bound states. And I want to actually, I saw comments in the chat that reproduction studies are never being published in the same high-profile journals. Well, in this case, it's actually different. The original paper was in Science, and this reproduction study, negative reproduction study, one may say, got published in Science as well. So here we have a positive case. And actually that continues because there is a second reproduction study of the same type of experiment, and that got published into Nature from the same team. Now, what is different here? This is a different type of measurement. Now, the device is the same. It's still this nanowire with the shell around it. But now we look at the length dependence of the devices. So you need to make many devices and shrink shrink their size. And what you look for is the energy splitting between zero bias states. So you have states that are at very low energy or at zero bias, and as you make the device shorter, they start to split. And the physical mechanism behind this is that they start interacting with each other, and Majorana fermions, when they start overlapping, they start, splitting away from zero energy. There is when you do that length dependence, there's a very specific prediction from a simple theory, namely that it should be an exponential decay. Whereas if it's non-Majorana, it should be a power law decay. This is already a methodological issue, I think, in itself, because you have very few data points. You can question what to do with these very small splittings. You can question what to do with very short length, because the theory is perhaps not applicable when you make devices as short as the wire diameter. So in the end, you are left with a bunch of data points in the center, 2, 3, 4, and you try to distinguish these two different dependencies. It's already not easy. But in the reproduction study, what is, I think, really a crucial find is that they found that in these vertical columns, they kept the length fixed. It is the same device, but they found a huge spread in the energy splitting between the states they were probing. Okay, and this is basically, it can go all over the place. And what is differing here? It is caused by gate tuning. So not the length. The length should be the one that affects the energy splitting, but no. It's changing the gate voltages here that actually hugely affect this energy splitting. So this measurement is prone to fine-tuning. The other thing they find in this reproduction experiment is that it does not need to correlate with a localized state here. And that is the simple picture with Majoranas, that you have them sitting at the end. And as you make the device shorter, they have to overlap and start to split. That picture is not applicable because they see these splittings in their measurements. They can measure that while not having to see local states at either end. So apparently this is a property of, somewhere in the middle or the bulk of the system rather than the localized end states. So these are all questions that I think apply to this, the second half of this paper, but also to two earlier papers. Okay. So what is the status here? I think the problems here are very similar to the Delft case, but we did not find the type of data manipulations in the Copenhagen work. Instead, we found cropping and we found crucial data omission. But the effect, this is why we think that this is perhaps the most crucial one. The effect is the same. The claims are unsupported. Now, I want to point at one of the satellite talks. There's a reproduction study being discussed there of another work from this team, similar in spirit, also nanowise, but a slightly different implementation. So the status is that the science paper, we think it should be retracted because it's not valid. We have concerns about multiple additional papers, but data requests are being consistently refused. So we basically cannot do anything despite, I think, valid concerns that we have. The last case I want to discuss is somewhat different in the sense that we have not done a deep investigation. It's a very complex experiment. It's been fairly recent, but I think it's important to discuss it here as well. So again, the device is very similar. It is a nanowire type experiment, very similar in implementation. And the idea now is to measure locally on this end, and look at the bulk of the system. So you want to see a zero bias state here, you want to see one here, and you want the bulk of the system to undergo a superconducting gap closing and reopening. And only when you see those three things together, you will conclude that you have found a topologically non-trivial phase with corresponding Majorana fermions. And this is formalized in a rather elaborate and complicated theory, also a fine-tuned theory that produces a protocol how to implement this. Fine-tuned, it has 25 or 30 parameters, so it's really one of these complex theoretical models. Now, two basic observations and things I want to point out. First is that the local measurements here are rather what we consider messy. You can see many of these bright vertical stripes again, which we tend to associate with localized Andreev bound state due to charge confinement, and then you get local Andreev bound states in these devices. Supposedly their protocol is robust against that, but I want to point out that this is all present here. So you can expect the trivial physics to play an important role here. The next thing I want to point out is that when they perform the protocol and when they find regions where all these three things happen, so where all the where the zero bias peaks and the gap closing and reopening coincide, this actually is extremely fine-tuned. The relevant range here really is the gate axis. This is about sub 1 millivolt in width, and this is the largest one I could find from the paper. Now, if you then have a conversion factor from gate voltage to actual energy in the devices, that's typically a factor 10, maybe 100 even. That depends how strongly it's coupled. So we're looking here at a feature that is tens, maybe 100, few hundred microvolt in width, which is really small in terms of localization physics. Quantum dots live on the scale of millivolts typically in these devices, in energy scales. So it's completely reasonable to me, at least, that as a consequence of this elaborate fine-tuning, you found the features you want, you're after, but that it could still be caused by disordered physics. And as a matter of fact, independent theory groups have been fine-tuning their non-topological models, and they can produce similar predictions. So this is not, we have not done a full analysis of all the materials available. Recently, they did share those. We did not get to that yet. There's a live journal club we did on this paper that you can find on YouTube. Those were the three case studies that I wanted to mention. Now I want to close basically with a few general remarks. So are the problems more widespread? This was really focused on nanowires, but there is a lot of research going on topological superconductivity and Majorana fermions. So there is another satellite talk, and I recommend you to watch it. It's also a notorious case, I would say. There the data was actually fabricated. It's about topological insulators, quantum anomalous Hall. So this was a very serious problem in another system. But more generically speaking, and I want to point at this disclaimer, this is not about particular papers at this stage. It's about generic philosophy of the research. I think many of these systems and many of the measurements we perform in them are prone to fine-tuning and biased data selections. For example, vortex cores are supposed to host Majorana fermions under the right conditions. How do you select which vortex to represent? How do you rule out trivial Andreev bound states? Interferometry with non-abelian statistics. It's a 2 decades known problem by now that it's extremely difficult to rule out Coulomb physics, electrical confinement related effects. Re-entrant supercurrent in certain Josephson junctions, sometimes associated with topological phases. But how do you rule out trivial effects? Shapiro steps to prove the 4-pi Josephson effect, another prediction of Majorana physics. Why is this also happening in trivial samples? What are the conditions under which this can happen? Can we establish actually, is it a valid method to claim Majoranas? So I think the situation is challenging and somewhat sad and worrisome. At the same time, I'm doing this because I care about research, although I'm not currently doing active research in my own team on the very topic. I still think it's beautiful physics that's worth investigating, and we should continue pursuing it. And in that sense, I'm an optimist. I think we can do better. So, and this is generic, I think, not only to this research field, but to all research fields. And many of the things have been said in the 2 previous talks already. So I think we should foster an open science culture, standardize sharing of full data, research protocols were relevant, analysis protocols, open publishing. So make the peer review publicly visible, at least the arguments, not necessarily the names, but at least the discussion. We should really normalize critical discussion, prior to publication, when something is shown at conferences, when the paper is in peer review on archive, also post-publication. Why are we not accepting a critical dissemination of work? Be critical of overly complex experiments. We have sometimes just too many control knobs, and it can lead to fine-tuning or overfitting. Verification and reproduction research. It's currently not funded, not really rewarded. Like you get some kudos for it, but it doesn't show on your CV really. But it takes a lot of time and effort. When you think there are problems, focus on the science primarily. Like that's the main thing we are after: establishing what science, what results we can trust, and how to move on. But ultimately, I think this requests a broader cultural change, some maybe even throughout society, not just in science. Less hype and breakthrough orientated, less single person, single team. It should be more collaborative. And I really hope we can, as a community, improve our work style and efforts there. That's at least what I will strive for. Thank you for your attention.
Okay, thank you, Vincent. Unfortunately, we've used up pretty much the whole time before the panel discussion. Let me just ask you one very short question, I think, if you don't mind. One, I think I understand from you, and correct me if I'm wrong, that to your mind, there has been no convincing demonstration of Majorana physics in any situation. Is that correct?
The honest answer is simple, yes.
Okay. Is there anywhere where you think that what is seen could be Majoranas, it just hasn't been proved? Or do you think that everything that has been demonstrated is ruled out by a skeptical eye?
Well, this is Occam's razor. I think it's a very healthy, normal principle. Why use the complex hypothesis if you have a simpler, more mundane one that we know for many decades that is around that can explain everything? Mm-hmm. But in principle, that is the problematic reason for it. That's why we bias ourselves. Why I got excited in the beginning of the PhD when there was much less awareness for all these problems. Of course, when we see the zero bias peaks, it could always be Majoranas, potentially. And that's why you start performing all the cross-checks. So you need to do in-depth, thorough experiments, look at the data as a whole, look at the full evidence, and then try and draw your conclusions based on that and share the full data. And accept it when later on it turns out that the alternative does also explain your data. Then go back in your feedback loop, basically. That is my attitude towards it.
Okay, any last burning questions before we get to the panel? Okay, if not, Vincent, thank you very much for a very, very nice overview. It's funny, I've heard many people claim that we have definitely observed Majoranas because there have been 12 papers saying that we do. And people don't realize how much work goes into vetting these things. Okay, sorry, one quick question. Gil Kalai asked, are there some attempts to study the Majorana? Sorry, there's some attempts. Okay, sorry, Gil, I guess I didn't understand your question. Is there some attempts to study Majorana phenomena that cannot be achieved? Okay.
Oh, if it cannot be achieved in principle, I think is what is meant here. I think it's basically impossible to answer that question in the sense that the toy models work. They are valid. We know that, and it's beautiful, rich physics in there. And under the right circumstances, it should be possible.
Let me jump in as a. Oh, go ahead, Gil.
No. I just. It might be possible that there are some physical reasons that you cannot achieve them. I should say that I tried to understand them and to model them using quantum computing, and I didn't find any such reason. But I do have some suggestion for reason in principle why topological qubit based on Majorana mode cannot be achieved. But maybe there are some other ideas why this particular state cannot be achieved in realistic physics situations.
Yeah, so since it's my field and I'm also a co-organizer, let me jump in one time during this workshop. So I think just the existence of Majorana is based on a very simple theory that must be true. However, it is a mean field theory that makes some approximations.
No, I don't ask if the theory is true. I just ask maybe there are some additional constraints on what you can achieve.
Yeah, so let me comment on that. So I'm aware of at least one work that I find interesting is by Tony Leggett from Urbana, where they look into this sort of non-abelian property, and as far as I understand, question that. So maybe just the basic topological thing can be realized, but who knows? Once we get to the non-abelian, and I think you also say the qubit might never be achieved. Who knows? Maybe we'll find that the actual non-abelian experiment is impossible.
Okay, so let me just point out that Tony Leggett is in the audience, and if you would like to comment, let me know. I will allow you to unmute. You don't have to if you don't want to.
Very. Can you hear me? Try to.
Yes, we hear you.
Okay. We in a recent paper we did in fact give some reasons why we believe that much of the analysis of Majoranas in two-dimensional P+IP Fermi superfluids, much of that analysis is based on mean field ideas, and we gave some arguments as to why the conclusions may not necessarily be valid if you try to go beyond mean field. If anyone's interested, it's in a new journal called Quantum Frontiers in the first issue of that.